Good afternoon, everyone, or good morning if you're from the west coast of Australia or in overseas as well. Welcome to this webinar brought to you by BuildingPoint Australia. Today, we're diving into an essential aspect of steel connection design, buckling checks, and how to apply them in IDS Statica. So buckling isn't just a strength issue. If overlooked, it can lead to costly design or even failures. That's why understanding and applying proper buckling checks is so important. In this session, we'll dive into how to perform and assess buckling checks using IDS Statica and enhance the overall safety of steel connection design. Let's get started. Before we begin, let me just introduce ourselves. My name is Bao-Lam. I'm an account manager at BuildingPoint, and I'll be one of the presenters for today's webinar. Joining me is my colleague, Nick Van Kreek, who is a sales and support consultant for our engineering products. For those who may not be familiar with BuildingPoint Australia, we are the authorized reseller for IDS Statica and also Trimble products in Australia and New Zealand. Our team focuses on sales, support, marketing, and training to help our customers get the most out of our solutions. For today's webinar, we'll cover a little bit about buckling checks and why they're essential in steel connection design. Then we'll go over some common buckling failure modes and how to prevent them. We'll also look into the practical approach using some buckling checks in IDS Statica and how the software helps with these checks. We'll cover some best practices for optimizing connection designs as well. And finally, we'll wrap it up with the Q&A session where we'll answer any questions you may have. So if any of you have any questions during the session, feel free to post them in the Q&A tab. We'll do our best to get to them at the end. And now I'll hand it over to Nick, who will take us through the buckling aspects of IDS Statica. All yours, Nick.
Thank you very much, Bao, and hello to everybody online live, and also welcome to those who may be viewing the recording later on. First of all, Bao, is my screen coming through clearly?
Yep, it's very good.
And I might just turn my camera off there to save a little bit of bandwidth. Okay, all right. Okay, IDS Statica. Just get rid of that little menu, I beg your pardon. Put up there. Preventing failure. The importance of buckling checks in IDS Statica. As Bao indicated, this can be very crucial, of course, for the success of our designs. And in supporting IDS Statica with our various customers for a number of years, sometimes I see quite slender elements included in the design. And so the buckling analysis is something that I talk about and suggest, and I think we need to have somewhat of a focus on buckling because we are, as engineers designing with steel, quite highly tuned and aware of the need for checking buckling for member design and frames and so forth. And so this failure of a bridge during construction in Canada illustrates perhaps some issue with temporary bracing or something like this. And clearly we have a lateral torsional buckling failure here. The same sort of thing, of course, could happen in connections. We could have a failure if we haven't paid enough attention to this issue. And it's less common, I guess, than member failures and frame failures. But the Interstate 35W Minnesota Bridge collapse in 2007 was largely attributed to inadequate gusset plates, and some articles there indicate it was they were too thin in respect to the buckling or the stability aspects. Other articles I read indicated it might have been failures, shear and ultimate failures of the plate, in other words, a stress or a fracture type of an issue. So there was potentially a buckling issue here as a major contributor to this significant bridge failure with multiple deaths and injuries in the United States in 2007. So we need to be conscious of the potential instabilities for members and frames. So, sorry, members and connections. So Idiostatica, it's a dedicated finite element application for steel connection design, and its headline capability is that it deals with general geometry and loading. So this is quite a breakthrough from previous methods, empirical methods, and software based on those empirical methods, which might have just dealt with specific types of connections, rigid connections, simple connections, and so forth. As you see in these couple of illustrations, we have some quite unusual, potentially unique, potentially complex connections. Idiostatica can handle them all. So that's the whole idea of using an FE methodology to generalize the solution, but then some clever approaches, I believe, have been used to check all aspects of the connections. And a key aspect of this is the first principles approach used for checking plates and sections in the connection. Other items such as bolts and welds and so on are checked using code expressions. If you've selected Australia, you'll get checks to AS4100, and we have codes from many regions around the world available in the software, Eurocode, American codes, Canadian, etc. So I'll be focusing on this first principles approach today. There's many other exciting aspects of Idiostatica, linking with other applications, the fact that it gives a complete solution and so on, but those topics could be perhaps for another time. So I just want to move to an illustration of a knee type connection. If I had a little bit of slope on the beam, this could be a knee in a portal frame. I could easily adjust the slope in the software, or it could be a regular floor beam or something like this, a horizontal beam as I have in this case. So I've added the members, the connection details, one load case, you can have as many as you like, and I've pressed calculate, which performs the analysis and gives us a summary of the result. So the question at this point is this connection okay? We see a number of green ticks. We don't see any red colouring in the overall check view. There's no failures indicated, and I don't have a red cross in any of the summary details at the top left. So the answer to the question I'd like to suggest right now is we don't yet know, because we haven't carried out the buckling analysis and made a review of that. And the buckling analysis is not quite as straightforward, perhaps, as some of the other checks given by the software. It's up to the engineer to make the review and make a determination of the adequacy in relation to instability. So today I talk quite a lot about the buckling load factor. That is a key aspect in the buckling checks with this software. Sometimes it's called the buckling factor or the critical factor, alpha CR. But essentially, the buckling load factor in this context is we have a component in the structure. I'm illustrating a column, of course, but it could be anything else like a connection. And I have some loading on it. In a connection, it would often be moment, shear force, axial force, and so forth. And so we have a loading combination and perhaps a whole series of those. So the component is loaded, and very often in working with Idiostatica, we're doing strength checks, and we are very close to the strength capability of the connection in some respect. It could be bolt failure, welds, plates, or whatever. So we're often talking about the strength limit state loading, and it's near to the design capacity of the connection according to some limit. And the buckling load factor relates to this design load that we have applied to a elastic buckling value or a value of load that will cause elastic buckling. So we're not talking about buckling with residual stresses or imperfections included and more complicated buckling like that. So we have a little bit extra margin in a sense in the buckling that we're talking about in Ideostatica, at least in the connection module, because we're talking exclusively about elastic buckling. So simply we have this elastic buckling load factor, which is, as I say, a key aspect of the buckling analysis and review. So just stepping back a little bit further, I guess, with the first principles methods in the software, because they both come into this consideration of buckling to some extent at least. But I won't spend that much time on the other key aspect of the plastic strain check. But this slide here is just to illustrate how we check sections or to the code. So, for example, we have a compact universal beam with major axis bending, and the design section capacity depends on the plastic section modulus. So clearly there's behind the scenes, in a sense, or the method set out in the code recognises ductility, and there would be significant plastic strain at the top and bottom flanges of this beam at the nominal strength limit state, where we have effectively full stress plastic stress blocks through the cross section to the neutral axis. So we see this sort of thing in many other areas of the standard, that we are looking at things like gross section yield and net section fracture in connections which might have bolt holes or eccentricities and so forth. And also in welded connections, we are utilising the ultimate tensile strength, down rating factors and so on. And there too, we have recognition in the standards of ductility and plastic strain. And very typically, historically, we have used yield line theory, plastic analysis effectively of an end plate in connection design. So both for steel sections and for connections, it's very commonplace to have significant plastic strain present in the nominal strength limit state condition or stress distributions. But let's look at how this is done in Ideostatica. If we put those same items in the software, a beam subject to moment, we'll see the extent of plastic strain in these plastic strain views and the results tables and so on. And the angle connected by bolts in tension, a little bit of eccentricity, net section a bit less than the gross section, we see some plastic strain occurring. And in fact, this is, in this case, very slightly over the limit. 1 kilonewton less actually made it just on the limit. So we're in a yielding plateau at this level. So a little bit less load can change the extent of plastic strain maximum quite a bit. And similarly, a universal column with bolt holes, we recognise there can be stress redistribution around bolt holes and so on, even if it's symmetrical like this. And we have the expression I mentioned before for the capacity to the code, or we can check the plastic strain in the software. And so too with welds, we see at different load levels some plastic strain developing at the ends of a longitudinal weld. And as we approach 100% capacity according to a hand calculation to AS 4100, in the software we would see the stress peaks at the ends relieving somewhat the loads to other areas of the world, but eventually we get full plastification in the software at 100% of load in this case. And instead of doing the yield line theory, we can just analyse the connection, the end plate, and make sure we don't exceed the plastic strain limits in the software. And the limit that is utilised in the software, it comes from the Eurocode. It was extensively tested, full-scale tests, research models, extensive validation, and this 5% plastic strain limit has been adopted globally in the software, all code regions, as a key limit for checking a very fundamental aspect of plate type elements, including parts of cross sections within the connection zone. So we have an elastic behavior of the steel material, up to Phi in Europe, but in Australia we have a 90% Phi factor, and so up to 0.9 times Fy. We then assume we have a yield plateau at a very low slope, and the key limit is the horizontal extent of plastic strain. That's, as I say, a fundamental aspect of the software which simulates many of the other checks that would otherwise be done to the code. And the other aspect of this first principles approach, there's two parts, A and B. The second is the consideration of instability. So first of all, let's look at how we consider this in standards. So we might have a cross-section type buckling considerations, local buckling. So we have B on T ratios to consider and grade. We have a modified slenderness and so forth, and various methods to determine whether the section is compact or non-compact or slender. We get the expressions set out, as I say, in the standard for establishing these design section capacities, including in shear. So this first one on the top left is in bending, local buckling due to bending. In the local buckling in the top flange, also bending, but local buckling occurring in the web in this case, and then shear. Also, of course, you have member buckling, lateral torsional buckling, axial buckling. I'm not really talking about member buckling much today because that's normally something to be considered away from the connections, but it might be something that comes up from time to time. And in fact, a later example, I'll show a consideration, in a sense, of gusset buckling as a member, in a short region. And also, if you have a knee brace, a short member in the connection, then member buckling could, of course, come into it there. But mostly we're concerned with short regions of members in the connection vicinity, a shear panel or something like this, and we are more concerned with local buckling on this topic. Sometimes the other buckling considerations, of course, including member buckling, come into connection checks, such as bearing checks and stiffener checks to the code. So, as I say, we have these methods for establishing suitable stability in our steel designs in a conventional way. But how do we do that in Ideostatica? The way it's done is we run the buckling analysis, we review the buckling modes and buckling load factors, and ensure the buckling load factors are high enough. So that's a very simple summary, I guess. Instead of all those complicated expressions and methods and so forth, we simply run the buckling analysis and make a review. But of course, unfortunately, the story isn't quite as simple as all of that. There's a couple of different conditions that we need to consider and make an informed decision about the buckling mode and the appropriate buckling load factor that we should meet for that mode of buckling. And so in the next couple of pages, I'll show you some references of where these recommendations that I've got in pink have come from. And mostly they're from the Ideostatica websites and so on. And there's one here which I've made as a summation, in a sense, based on a change of restraint, but I'll come to that shortly. So it used to be, if we sort of step back a couple of years working with the software, that we would just use two, or just have two limits to consider, 3 and 15. And so there's a few extra things that have come in the meantime due to some additional research. But mostly we are looking for a minimum buckling load factor of 3 in connections. That's still the case. There's some research that suggests that for a shear panel like this with stiffeners or plates on all 4 sides, that you could go as low as 2. So there's a relaxation in that situation. I haven't done work myself on that, so in the meantime, I'd like to just keep to 3 personally for that one. But if it's going to have some significant cost implications for you and benefits, by all means, look into this further if you have a situation like that which has a buckling load factor less than 3. But for stiffeners like this and other general situations in a connection where we have buckling modes showing up, we want to go to at least 3 as a buckling load factor. Another special case to mention is a two-sided triangular type connected element, or I guess the main condition is it's a two-sided connection. And there the recommendation is to look for a little bit more, a buckling load factor of at least 4. Now, for a gusset connected member like this, there's a possibility, and in fact, I think the strut very often wants to sway. So we have to be on guard for this situation in particular. So the typical situation in the software is that the right-hand end of this circular strut will be fully restrained in the buckling analysis, and it can't rotate and it can't sway either. And in that case, if the gusset is to buckle, it will buckle in a half buckling effective length. And with the inverse square law, this is effectively multiplying the buckling load factor by a factor of 4. So that's why 15 is roughly 4 times the typical buckling load factor in my view. That's why we look for such a high target in this situation. But depending on some settings that we utilize in the software, and we'll need to, I'll discuss this later, we might allow the sway, we release the sway restraint or expose the sway mode of buckling. And in this case, I think we could go to about a quarter, so back to the usual sort of values. And that's why I'm indicating approximately 4 would be sufficient for this situation where the real sway type of buckle could occur. And as I say, we really need to be on guard with this. The Australian Steel Institute, about 20 years ago, tightened up their guidelines and their design guides around this issue because there was some real failures in service using a longer effective length for that gusset zone. So we need to be quite careful of this one. All right. So just a little bit more on where these things have come from. So first of all, from this article from Ideostatica's website, there's a comment. The result of buckling analysis in Ideostatica is not a definite check. The codes do not give sufficient guidance, and the assessment requires engineering judgment, and Ideostatica provides unique tools not available in standard design software. So I think that's very true. We do have a very advanced and a very practical design tool, a tool here in Ideostatica for daily use. Typical structural engineers can use this to make their strength checks, including a buckling analysis and so on. But at this point, as I say, it's not quite as clearly defined, and the software doesn't give a green tick or a red cross as a pass or fail. Maybe in the future it will, but for now we have to make a judgment about these things. And so from this article, we'll see the various situations I've described in the previous summary discussed. So if we have a gusset connected member, and this will be the typical case with full restraint of the strut in the buckling analysis in the software, that we need to have at least 15 as a buckling load factor, but otherwise a minimum buckling load factor of 3. So these are earlier articles and so on. Now, there is an article I'll come to later which discusses a change in the restraint arrangement for buckling, depending on the model type, the setting that we utilize. I'll come to that later. Some more recent articles in the Ideostatica website in relation to buckling have added a little bit of nuance and some extra detail here. So this article talks about a 4-sided restrained plate element, such as a shear panel. And in this case, there is this relaxation of the buckling load factor could be as low as 2. If we have a gusset type buckle, just discussed, we want at least 15. If it's a typical stiffener like this one here, most aspects of connections, in fact, I find we need to look for at least 3 as a buckling load factor. but there is the two-sided or triangular type stiffener where at least 4 is asked for. And this factor of 4 has come from some American research. We'll send you these links to everybody who's registered, so you can quickly go to these various articles. But this research has indicated for load resistance factor design, so similar to Australian limit state design, we should have a buckling load factor of at least 4. So something to be aware of, I guess. All right, so we're starting to talk quite a bit about buckling load factors, and I thought it might be worthwhile to look at buckling load factors for steel members. So we're very familiar with designing universal beams and welded beams in structures. What are their local buckling modes? And so for all of the standard grade 300 sections, I applied the design section capacities in bending, compression and shear, and looked at the lowest buckling load factor for local buckling. Sometimes member buckling showed up as the lowest factor or a lower factor. I disregarded those. So in the following results, I've disregarded member buckling. It's, as I say, not of concern for the local connection vicinity for the current topic. All right, so UBs and WBs in bending. And just to illustrate the different sections, I've got the mass per metre along the bottom axis here. So we go from a 150 UB 14 up to a 610 UB 125. So these are the orange dots here for universal beams. And we see in bending the lowest buckling load factor for local buckling is about 3.7 or so, and we're averaging about 6, I guess. So the ratio of the design section capacity in bending to the elastic buckling load, the bending moment associated with that. Excuse me. And it seems like the webs play a big part in even the bending buckling mode, but the plate and the web, of course, are an assembly and they're buckled together. For welded beams, the buckling load factor is typically about 4 or higher. Sometimes it's a little bit less, and as low as 3.36 for the 800 WB 122. That's quite slender. Now we come to compression, UBs and WBs, and I was somewhat shocked, and I of course checked this multiple times to see the buckling load factor for WBs in axial compression is often very low, down around 1 or even slightly less, and in the case of a grade 400 section, it was about 81%, a very slender one, and I didn't graph that here. But for UBs to axial compression, we go from about 1.5 buckling load factor up to about 3 or 4, a couple are a little bit higher than that. But as I say, for WBs, the buckling load factor is very low, about 1 to 1.5 or so. And having a think about this, I thought, well, this is a little bit like a purlin type section, perhaps. We perhaps have some post-buckling capacity or consideration built into the expressions in AS 4100 here. So we typically with WBs have quite big flanges and quite a slender web. And so if you put that in as a column, it's the web could buckle, but we've still got the reserve in a sense, or we've got those big flanges there. So that's perhaps why we have such low buckling load factors there. And they would typically be used for bending or even as columns in portal frames, largely for bending purposes and stiffness and so forth. And if you have largely a dominant or a dominant compression load to carry, you wouldn't tend to choose a WB, would you? All right, now moving on to shear, and the buckling load factors are again quite low for WB. But for UBs, we've got some a little bit higher than 2, but we're typically around about 3 to 5, I guess, for the minimum buckling load factor for shear. But for WBs, it gets down to about 1.3 or so, up to about 2.6, looking at the range there. So we see that buckling load factor is not a uniform value. The sections haven't been designed to achieve that, I guess, and some are clearly there. It's quite heavyweight solutions and so on. Others are there perhaps more for lightly loaded structures, or with bigger spans and things like this. So there's no real reason why there should be a consistent buckling load factor. But as mentioned before, in Idea Statica, we are looking for some minimum values to satisfy this stability aspect in our connections. So I just wanted to look at a plate outstand, like a flange or a vertical stiffener on a beam in a connection vicinity, and just go back to some fundamentals here. And just as a bit of an exploration of, in relation to whether these values of 3 or 4 as a minimum buckling load factor are high enough. So looking at the Timoshenko buckling stress and so on, it uses the B on T, or the inverse here. So B on T, the width to thickness ratio, and of course the typically in our code, we modify that with the yield stress calculation compared to 250 as well. But getting back to Timoshenko's fundamental critical buckling stress, it depends on support conditions of a plate in compression. So here we have a flange type situation, or a stiffener like this, where it's simply supported on one side. Theoretically, there might be some rotational restraint, but assume we have uniform compression simply supported on one side and the other side is free. And if we have a very long plate, like I did in the software here, with one side vertically restrained, laterally restrained, simply supported, the buckling coefficient is as low as 0.425, and the buckling mode half wavelength is infinite. And so as I could make this plate longer and longer, and I'll get this full half wavelength over the full length. I saw that in the software when I did some experiments. But if we have simply support on both sides, like a web, either as a column or even a bending moment, we're going to have some differences creeping in. If it is uniform compression, this is a bending situation by the look of it. But if we have uniform compression, the buckling load factor, or the buckling coefficient K for this expression, is quite a bit higher, but the B on T ratio is generally quite high, and this is the inverse, so a very low contributor to this expression. And something that's important here, I think, to recognise is that the buckling half wavelength for a web type situation is the depth of the section, or the net depth of the section. So we see that the section likes to buckle with a half wavelength approximately equal to the web depth. And this is forcing the flange, because it's an assembly of plates, to buckle in sync. And what we saw with the first situation is that if the length is a little bit less, the buckling load factor goes up a little bit. So the flange being forced to buckle at a shorter wavelength, or half wavelength, tends to increase the buckling stress in the flanges, the flange outstands, or a stiffener on top like this. So just sort of, as I say, a bit of an exploration of what's going on there, because this stiffener situation is very key to many connection aspects, or many connections in Idea Statica. So let's have a look a bit further at this. We have our elastic and plastic material property, and for the full 5% plastic strain, we'll get an extra 10% stress compared to the 90% yield here. So putting all of these things together, if we have a buckling load factor of at least 3, then I'm going to take the Timoshenko stress for this plate divided by 3 and superimpose this on a graph with the maximum stress for 250 grade steel, which is 0.9 Fy plus 10 megapascals. And so if we're working with an outstand or a stiffener, something like this, we would need to be below the horizontal blue line and also below the Timoshenko stress divided by 3. But we're not quite doing it like that in the software. We're analysing the entire connection and doing a buckling analysis of the entire connection. So I thought maybe sometimes if we have a flange outstand that is a little bit wider than a compact type situation, that this might try to destabilize the other plates, the connected elements and so forth. So a little bit more on this graph. 15 to 1 is the maximum stiffener slenderness. It's modified if it's not grade 250 slightly, but essentially 15 to 1. So for a 10 mil thick stiffener, we could be 150 wide. This is bearing stiffener limits in AS 4100. And if we look at beams in bending, and if they're compact, we can have a B on T ratio of 8, or if it's hot rolled, 9. So anything less than the compact limit, buckling should not be of any concern, and we shouldn't be to the right of the vertical pink dotted line here. And so we're going to be in this zone typically here. But what if we are expecting some plastification of our stiffener that is at the limit, up at 15 to 1? And that's, as I say, what I thought I might just look into a little bit further. Now, we saw earlier that a 800 WB 122 had a buckling load factor for bending of 3.36. So that was the lowest that I found in all the standard sections. So I applied this with a 180 by 12 stiffener, grade 250. So that's on the slenderness limit. And I made the stiffeners a bit longer than usual just to see if I could make it fail, in a sense, in terms of plastic strain or buckling. It was very difficult, I found, to get enough load into this region. Either the beam tended to fail outside the stiffener, either in plastic strain, or the buckling modes were showing up in that region. So based on that, I concluded that, at least on that one test, that even though the 15 to 1 is more slender than a compact outstand to 4100 for a beam that could undergo significant plastification at limit state, nominal limit state moment level, we still don't see a problem developing here because of the assembly of plates and these factors I mentioned before about the plates buckling in sync, and we have stiffening effects from the vertical plates and so forth in the connection vicinity as well. So even though on first appearances, anything above about 10.5 up to 15 might have looked like the buckling wouldn't allow some yielding, when you put all of the items together, it seems to be that things are fine. So this has been taken into account by the look of it in the indicated buckling load factors for stiffeners and flange outstands and this sort of thing. All right, so let's get back, putting all of these things together. Let's have a look at the software finally and get back to this question of, is this connection here? Okay, so I'll switch across to the software. And here it is. I've set up the connection. I've pressed calculate and I've got the results, 30 seconds later or something like that. And as indicated before, we haven't carried out the buckling analysis. And, up to this point, I've tried to be, very clever in a sense of using quite thin elements and so forth to save money and small welds, etc. Really trying to make it a very economical solution, but clearly there is potential for a problem occurring there. So from the design tab in the software, we don't have the opportunity to select the buckling analysis. We need to go to the check menu and then use the drop down on the calculate. we can do the regular stress strain analysis, or we can run the buckling analysis as well. So that's what we need to do in these situations. I would say, even if your connection is quite compact, appears to be quite compact, and you're not concerned about buckling, it's not difficult to, at least at one time, run the buckling analysis just as a confirmation. And you might get buckling load factors of 15 or 50 or something like this, depending on how heavy and compact it is. But as I say, it's not difficult to run the buckling analysis. And now we see the minimum buckling load factor that the software has identified. And we could, in the normal way, go through and have a look at the von Mises stress views and all of these normal things. I won't spend much time on that, looking at deformation and the performance of the connection, subject to the moment and shear and so on. The plastic strain that's developing, it's not exceeding the limits. It's very close in some location. We can look at contact stresses that influences prying effects and so on in bolts, but we're interested in the buckling results here. And I'll select the buckling shapes, and we can select the buckling tab over here. And if we want more than the default 6 number of buckling modes for each load, we can go to project settings and select model, and here we can increase or decrease from 6 to the desired value, anywhere from 3 to 30. And sometimes we need to do that to show some more buckling load factors than the default. So here we have a buckling mode just below the stiffener, just below the connection, at a buckling load factor of 1.45. And we saw with WBs earlier that if they're just in compression and in bending also, that we have some relatively low buckling load factors. But we could have some influence from the connection here, and I think there is. We could perhaps set this up if we wanted to see if that buckling mode was going to happen anyway without the connection influence. Maybe set up a different model where we're not applying concentrated stress at that location. Perhaps we set up the loading slightly differently and see if the member wants to buckle just the same way, or maybe it doesn't have, maybe it has a much higher buckling load factor. So we can make some assessment about if the buckling mode is in the member away from the connection, is it being sufficiently influenced by the connection to be of concern? So that's something that comes up a bit. But we see in the von Mises stress that the compression and the shear developed or delivered by the connection to this zone is causing significant stress concentration here. And I would say that there's a potential effect on the buckling of the column there. We could also look at some other views and so forth, but that's something that I would tend to do to try to determine whether it's a connection factor, or is it just a member factor that would be checked by other things. But we're also seeing some buckling in that stiffener, perhaps in sympathy with that wet buckle, but this is quite a low value, so I would be concerned, and I need to increase the stiffener thickness and so on, make some changes here. And we can proceed through the different modes. We see a shear buckle here. There was an indication that maybe that could be as low as 2. We're less than that anyway, and so on. And clearly we have some issues with this connection. As I say, I've made it deliberately thin and stiffened the buckle there, less than 3. We're still less than 3. So all of these, unless it's well away from the connection, are going to be of concern, I would say. So of course we make the changes and we rerun the buckling analysis and satisfy ourselves, and then at that point we could select the report and so on. All right, another connection that we might want to look at is a strut connected member, and let's have a look at this a bit further. Time is tight as always, but a gusset connected member, as mentioned earlier, there's some settings that influence the restraint in the analyses, so both in the strength analysis and in the buckling analysis. And so from the reference, well, as I say, we'll send it to you. If you use the first model type in pink, that provides zero restraint to the outer end of the member in the strength analysis, but full restraint laterally and rotationally in the buckling analysis. That's the default setup. But sometimes we can't do that. Sometimes we need to offer some restraint for the strength analysis. We might get, due to eccentricity, some too much lateral bending, or we might have a single bolt connection and we need to provide some restraint to prevent an instability. So sometimes we need to select one of the other model types to provide some restraint in the strength analysis. And that changes the buckling restraint. It allows the sway mode to develop. And this is all explained in this article here. Let's go to the software and have a look at that. So here I have the setup. I've been quite casual in the way I've set up this cleat. It's very long. The spacings are too big. This is not good practice, I would suggest. We need to be a lot more careful about this and make it short, these areas that could potentially buckle. So we would have checked this CHS for the effective length between the supports for compression buckling and so on. We expect that we're not going to have problems in the connection, but we have to make sure, of course, that we don't. But here again, I've done the analysis without considering the buckling, and if we just stop there, we might feel that we have sufficient capacity and so forth. But let me just go back one step. If we haven't made a change to this, well, perhaps while I'm there, we'll see with the stress view and deformation that we don't get much lateral sway because I have introduced a model type that provides rotational restraint here, and so it can't completely rotate around. So this would be appropriate for a strut like this. And the buckling mode is not calculated, so I can come back to that or go to the PowerPoint. But if we don't change that model type, if we start like this and we put our loads on and so on and press calculate without doing a buckling analysis also, we'll see that we might have some problems. The eccentricity of the plates, it's the small eccentricity, but that coupled with the significant compression can cause too much lateral deflection. And in fact, we've got excessive plastic strain here. And when we look into this, we'll see that there's a lot of lateral deformation. It's not a very high scale of 6, but even 3, it's showing a lot of issues there. So this is why we, in a situation like this, we would select this member and set a different model type to provide that rotational restraint here. But as I say, this now changes the buckling load factor, changes the restraint in the buckling analysis, which therefore has an implication on the buckling load factor. And there's another situation like this, I'll go to quickly, which is a single bolt connection like this. And again, this comes up in support a bit. We have the connection all set up, but the analysis iterates down to 0 essentially. Well, it's because there's a rotational instability about this bolt. And so what we need to do is, again, select a suitable model type, which would be perhaps the 4th one. I think I've got that here in the second connection. And in this case, the analysis completes, but for the buckling analysis, we will see the exposure, in a sense, of the lateral sway mode and depending on mesh and deformation. So we see the sway mode exposed, which is what can happen, of course. Even if the other end is fully welded to a solid support, it would be quite long. In general, would not be able to prevent sway here if this connection wants to buckle. So, but in this case, with sway exposed, I would look for at least 4 as a buckling load factor, and we've got more than that. So I would be satisfied with that result. All right, that's essentially it for the PowerPoint, except to just show briefly Some other references, if you're interested in bearing stiffeners and so forth, lots of good articles on the Ideastatica website. Also in the Australian Steel Institute Rigid Connection series, authored by Tim Hogan, there's some detailed information about design of stiffeners and limits to slenderness and so forth, and also for bearing stiffeners. And something that I thought was quite interesting, when we read AS 4100, it suggests a mandatory limit on the slenderness here, the 15:1 roughly, depends on grade, as I say. But in this design guide, there is some scope, I think, for having a more slender stiffener, as long as you only consider this as an effective width. So you could perhaps go slightly more slender than that, but you've got to be quite careful, I guess, about the slenderness and the buckling there. So that's it. Thank you for your interest, and I'm happy to take any questions. Thank you very much.
Yeah. Thanks, Nick, for the in-depth presentation on buckling checks in steel connection design. We now have just a few minutes to answer your questions. So post them up in the Q&A tab. I think I saw that we had 2 questions to begin with, one from Chan. He's asking about how the software deals with minimum design actions according to AS 4100, which I've replied to, saying that it's up to the user to enforce those actions and check that all the load combinations complies with AS 4100 before analysis. But there is a little workaround in the software where they've introduced the percentage loading as a workaround to apply the minimum design actions in the software. I don't know if you want to just quickly show that, Nick, the percentage loading.
We could do that, yes. Okay, so I'll share my screen. Let's go back to that and escape on that. So if we are putting in loading in the software, but yes, I agree with you. And I mean, it's a very good question. The software does not provide for that, but if we are setting up loading, we could toggle the loading to load percentage. And so if we wanted to make sure for this member, this is member 2, that we had a certain amount of loading, percentage-wise of, say, axial tension capacity, we could put in that value, for 80% or something like this, and it will actually turn into, so many kilonewtons. So, but we have asked for minimum design actions to be automated. Now, it's a bit of complexity, so it depends on the type of connection. Is it going to be a simple type of connection, a compression connection, column splice, and this sort of thing? So the code gives different minimum values, percentages, or absolute values. So we might need some radio buttons or some options to tick that you want it to be this or that connection, and then set some minimums. But because of the total general nature of the software, that has not been implemented. I think it is a difficult thing to set up and for the software to make those assumptions, if you like. So at the moment, it's up to the engineer to make sure those are included. I think most of the time, the minimum design actions will be less than the actual loads that you've entered. But yes, as I say, good question, something for the engineer to ensure they're covering off.
Yep, thanks, Nick. And just another last question as well that we have time for. Question from Alessandro. What are the lengths of the UB and WB used for the buckling load factors? So I'm assuming he's referring to your slide, Nick, earlier.
Yes.
On the UB and
the
WB.
Lengths, it was a multiple of the depth or the width of the member, the depth in all cases, for the case of UBs and WBs. It was about 8 times the length of the member for bending moment and axial compression, and about 3 times the length for shear. Because for shear, there's an inevitable bending moment that occurs, and so I didn't want to make those members too big when I applied shear loads. Otherwise, we would get some bending buckling load factors showing up at the ends of those members where the moment is high. But the length is not particularly important as long as it's long enough, I guess, so that you get those local buckling modes exposed.
Yep. Thanks, Nick. Yeah, just the remainder questions we'll just reply to privately. Just before we wrap it up, I just want to mention a few key takeaways. So the recording itself will be uploaded to our BuildingPoint Australia YouTube channel. So if you haven't subscribed yet, we encourage you to do so. Also, if you're new to Idea Statica and would like to try it out, you can activate a free 2 weeks free trial from the website. There's also a self-paced campus course to help you get started with the first steps with the software. And we also have a support center available that offers plenty of resources, including tips and tricks, theoretical background, webinars, and more, all available on the official ideastatica.com website. If you have any questions for myself and Nick, just get in touch. And I'd like to thank everybody for joining us today. Have a good day onwards. Thank you so much.
Thank you very much.